Hello. Good afternoon, my dear student. Today we will discuss about transient response of a RLC circuit in presence of a DC excitation. Okay, today we will focus on the transient response of a RLC circuit in presence of a DC excitation. So far, in our previous classes, we have studied and discussed about the transient response as well as steady state response of RL and also RC circuit in presence of a DC supply voltage. You have noticed that a circuit consists of only R and L or R and C can be described by a first order differential equation. Let me repeat this point. A RC circuit or a RL circuit can be described mathematically by a differential equation, by a first order linear, first order ordinary differential equation, maybe homogeneous or non-homogeneous. Okay, but today we will discuss about the response, especially transient response of a RLC circuit. That means our circuit containing resistor, capacitor and inductor. Okay, so this such type of circuit can be described by a second order linear differential equation, by a second order linear ordinary differential equation. Okay, so the basic or fundamental difference between a RC circuit or a RL circuit with a RLC circuit is that RC circuit or RL circuit can be described mathematically by a first order differential equation, but for the RLC circuit we need to use a second order differential equation because the circuit having two energy storing element, one is inductor and another one is capacitor. So now I suggest all of you the write the differential equation for this circuit using Kirchhoff voltage law, because we know that if we use Kirchhoff voltage law, then the transient response in terms of current or voltage can be easily computed. Okay, so let me write the differential equation, second order linear, second order ordinary differential equation for this circuit, because we will first to derive or compute transient response or steady state response. First step is to express the system, KVL, total voltage drop across a closed loop using Kirchhoff voltage law. So first, let me write the Kirchhoff voltage law for this circuit. So say one thing, let me tell you. You see, here is a switch exists between the supply voltage and the one terminal of resistor component. You see, and this switch is connected at t, just t equal to 0 or t greater than, just actually t greater than 0. Okay, little bit slightly. Okay, so we have connected the supply voltage with this circuit through this switch at t equal to 0 or slightly greater than 0. Okay, at t greater than 0, not equal to 0. We consider at t equal to 0 the switch is open, but at t greater than 0, just t greater than 0, the switch is connected. Okay, so now let me write the Kirchhoff voltage law. By applying, everyone write the Kirchhoff voltage law equation for this circuit yourself. By applying KVL, KVL for this circuit, we can write the supply voltage is denoted here by a symbol V subscript S. So Vs is nothing but the supply voltage equal to the voltage drop across resistor R, the sum of voltage drop across resistor R, voltage drop across inductor L, and voltage drop across capacitor C. You see, we have considered here that the current through this circuit is I of t. So therefore we can write the voltage drop, suppose across R, VR, plus voltage drop across inductor is VL, and voltage drop across capacitor, it is given here VCT. VC of t. These all are in small letter, you write, change with time, no problem, you can write. Okay, you consider. Okay, so VC t. Now we can write this voltage drop as a product of the current and their corresponding properties, I mean resistance, inductance, and capacitance. So everyone write the expression of voltage drop across R, across inductor, and across capacitor as a product of current and their properties. So let me write it. We can write VR equal to I of t into R, plus VL equal to, we can write, L T I T Y dt, and voltage drop across capacitor is VC. Here we have considered VC, and all are function of time. Okay, if you write, no problem, if you write it's good, otherwise it implies that these all are function of t, time function. Okay, all are function of t. Now our next task is to find out the homogeneous or differential equation. I mean, we need to compute the transient response for this circuit. So first we will make it as a standard form of second order differential equation. You know that first, you see, this is a first order differential equation, but we know that the voltage drop across capacitor or the current I of t can be expressed in terms of voltage drop across capacitor. We can write the expression of current in terms of voltage drop across capacitor, because you know that current is nothing but the rate of change of charge, I of t equal to dqt by dt. Now you can replace the charge in terms of Cv. So d dt Cv. So ultimately you will get d square t dt square di square t dt square Cv. So let me write it. We can write I of t equal to, actually one thing, let me tell you, you can find out the expression of transient current for this circuit, I mean I of t, or you can find out the expression of transient voltage. However, in this case, I have considered the transient voltage part. Okay, but you can also calculate, you can also solve this equation in terms of current. Okay, then you change the Vc in terms of I of t, but in this case I have changed the current in terms of voltage. I can calculate the transient response of the voltage drop across capacitor C. So let me, and if I get, then I can calculate the voltage, transient voltage for R inductor. Okay, no problem. So let me write it d q charge dqt by dt, and this thing we can write, we can solve this thing in two way, either by considering I of t or by considering Vc of t. So here I have considered current in terms of Vct. So let me write it d uh, qt equal to, I can write c Vc of t by dt. Okay, so this is our c. This will be capital. C is capacitor is capital. Okay, so therefore we can write this thing. So ultimately you will get C is a constant capacitor value is constant. The C will be taken outside of the derivative part. So we will can write C d V C t by dt. Okay, if you have any confusion to understand this point, let me know, or you write in your chat box about your confusion. Therefore, we can write I of t in terms of Vc, the voltage drop across capacitor, as I of t equal to C dVct dt. Okay. Okay, if you have any confusion or you face difficulty to understand this point, write your confusion in the chat box. Now we will replace the value of I of t in our previous equation. Suppose this equation is 1, equation 1. Right? This is suppose equation 1. Equation 1. You write this is equation 1. Okay, now you replace the value of I of t, just substitute, you substitute the values of, substituting the value of I of t into equation 1. Okay, so then we can write V is equal to I mean RC dV dVc t by dt plus we can write LC 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 d square VCT by dt square plus we can write VCT. Okay, so let me write it in the proper format. D square VCT by d square. Okay, everyone see the final expression. and you solve it yourself. Okay. Now we will simplify this thing actually uh, as a homogeneous equation. Actually our objective is to calculate. Can you repeat the I of t equation, please? Pal, I of t, you know the current is nothing but the rate of change of charge. We know that I of t equal to dqt by dt, where q is the charge. And you know charge is equal to the product of capacitor voltage and capacitance. The product of capacitor voltage and capacitance, Cv. You know C is constant for this particular circuit. This is the value of capacitor. You can consider 5 nanofarad, 10 nanofarad. That means the value of C is a fixed value or a constant value. So therefore we can take C capacitor value is outside of the derivative. If you take derivative of the C, then you will get 0. So you know d dt of uv, you will get u dv dt plus v du dt. If one term is constant, then you will get only one part. Okay, or three. So according to that approach, we have written I of t equal to c dv c t by dt. Okay, thank you. Uh, now now, our objective is to study the transient response for this circuit. For this actually equation. For this equation is a differential equation, second order differential equation, and non-homogeneous, because there is a means supply voltage. There is a supply voltage in our circuit. Okay, so therefore this is a non-homogeneous second order differential equation. So the solution of this equation, if you consider the form of a standard second order differential non-homogeneous differential equation, then you know that equation, the complete solution has two parts. One is its steady state response and another one is its transient response. Actually solution of this part, let me write here. Solution of this equation, solution of this equation has complete solution. Actually I mean complete solution consists of, complete solution has two parts, has two parts two parts. If complete solution is, suppose Vc of t, then you will get two solution. I mean steady state response. Suppose steady state response is supply voltage will be steady state response. Let me write here steady state response plus transient response. And you know that transient response will disappear after a certain time, and that time is equal to 5 time constant. Okay, after 5 time constant, transient response of this circuit will die out or disappear or becomes 0. But after 5 time constant, the response of this circuit reaches to its steady state value. Now our objective here is to find out the transient response, not steady state response, because we know that steady state response for a circuit will be same as its supply voltage. Okay, so now our goal is to calculate this transient part only, transient response. This part will be equal to the supply voltage if you solve it. So our objective is to calculate the transient response. Transient response. Okay, this part we will calculate it. I have marked it as a red color, by a red color. So now we will calculate this part. Okay, to calculate the transient response of a circuit, we know first we will convert the non-homogeneous equation into a homogeneous equation by by replacing supply voltage or supply voltage, I mean, to make supply voltage equal to 0. So let me write this point. Let me write here. Okay. Let me write here this point. Our goal is to here the objective or goal. Our objective objective is to compute the transient response of the RLC circuit. Okay, transient response. So to obtain transient response, first we will convert this non-homogeneous equation into a homogeneous equation by considering V is equal to 0. So let me write it. So to to convert the non-homogeneous equation into a homogeneous equation. Okay, homogeneous equation into a homogeneous equation. So how do we convert it? We will make the just Vs equal to 0. So let me write the equation. We will just let me copy this thing. Okay, equal to 0. Okay, here we have made V is equal to 0 since V is equal to 0. Okay, everyone, try to understand this point. This is the crucial point for solving this equation. To compute, we know that the differential equation whatever we have obtained from this RLC circuit is a non-homogeneous differential equation, second order differential equation of VC. If we solve this equation, then we will get a complete solution in terms of VC. And this complete solution has two parts. One is steady state response and another one is transient response. And you know that steady state response is nothing but the supply or external source voltage. So for this case, steady state voltage will be Vs. And on the other hand, transient response, we need to compute the transient response. To compute the transient response, you first convert this non-homogeneous equation into a homogeneous equation by considering Vs equal to 0. Okay, now we got a linear second order homogeneous differential equation. This equation is known as homogeneous. Actually, you see that everyone, I hope you know the basic difference between homogeneous and non-homogeneous equation. Let me repeat this thing. Homogeneous equation actually is part of homogeneous equation consists of a particular variable. You will see that VCT, and its right hand part is equal to 0. But non-homogeneous equation, there is a non-zero term present at the right hand side. Okay, at the right hand side, this sum will be not equal to 0, will be equal to Vs, Ka, whatever, not equal to 0. Then we can say that is the non-homogeneous equation. This is homogeneous equation. I am telling you this point many times because we know that the solution of a homogeneous differential equation is nothing but a1 e to the power alpha t plus a2 e to the power alpha 2t, alpha 1t alpha 2t, where alpha 1 alpha 2 are the roots of its characteristics equation. Okay, let me solve this equation first. Okay, so first what we will do it, first we will make it as a standard second order differential equation. So let me write the standard differential equation. So the everyone write yourself the standard form of this differential equation. uh, Let me copy this part from here, this part, plus we can write RC divided by LC. So CC will be cancelled out, we will get R by L. So therefore we can write plus RC divided by LC, we will get only R by capital L. R by capital L, you make it, you put it within the bracket. Okay, and then we will get uh, 1 by LC. I mean VCT by LC equal to 0. Everyone look at the equation and you write this is equation 3. Equation 3. However, we can solve this equation easily by using Laplace transform, but after covering the Laplace transform, we will solve this problem for AC response, and that time I will discuss. We can solve this problem easily by using Laplace transform. Okay, but now you try to solve this equation in time domain. Actually, Laplace transform help us to solve a problem in frequency domain. I will discuss that part later on. Now you solve this equation in time domain. If we solve this equation in time domain, then the calculation part is a little bit complex compared to it solved in Laplace domain. Amit, I will provide some sample question for MTA exam by tomorrow or day after tomorrow. Don't worry, I will provide you a bunch of sample question for MTA exam by tomorrow or day after tomorrow. I mean within 2 days. Within 2 days, I will try to provide a bunch of sample question for MTA exam. Now everyone can solve this equation because this is a standard form of second order differential equation. So therefore the solution of this equation without rigorous calculation, let me write the solution part for this equation. VC, you solve it yourself, no problem. VCT, the solution VCT for this equation is equal to suppose capital A1 exponential term of alpha 1t. Alpha 1 is the actually roots of this equation. So first, let me write this thing in a simple form. So in characteristics equation, so you consider that the coefficient of first term is coefficient of first term. This is first term, then second, then third. First term is first term for this equation, first term is suppose a and a equal to 1. Let me write it. And for second term, coefficient of first term for second term, second term suppose b equal to, you see, r by l. And third term, coefficient of third term is suppose we consider a b and you consider small c equal to 1 by LC. Okay, the coefficient of this first term is suppose a equal to 1, you see that 1, and this is b r by l, and this is c, and you consider you consider that d square dt equal to alpha. Let me write this thing. Let me take this symbol. Suppose alpha, you consider alpha equal to d by dt, then you can write alpha square equal to d square by dt square, alpha square equal to d square dt square. Okay, alpha square equal to d square. Actually we will make it as we will actually compute its auxiliary equation, characteristic equation, characteristic equation. So if I write characteristic equation of this equation by putting this value, we can write, let me write it here, the characteristics equation characteristic equation of equation 3, characteristic equation of equation 3 is by putting this value. Okay, is we can write this is equal to alpha square vc. So alpha square vc, alpha square v sorry vc of t. This is alpha square, not alpha. Now you write auxiliary equation for this circuit. Auxiliary equation for this circuit. Sorry. Alpha square VCT, then you can write plus alpha VC VC of T plus VC of T equal to 0, and you put its coefficient. For this case will be a B, for this case will be C. Okay, now you take VC is common from this three term, then you can write alpha square plus B alpha plus C equal to 0. Alpha square plus B B alpha alpha square plus B alpha plus C equal to 0. B alpha. Everyone try to understand this point. To solve this equation, we need to take help of characteristics equation. B alpha plus C equal to 0. Okay, and you make it alpha square. Alpha square. So now we can solve this equation using the standard formula. So alpha, the value of, therefore the root of this equation, the roots of this equation have two actually component, alpha 1 and alpha 2. So alpha is equal to, we can write minus b plus minus b alpha plus minus, we can write what will be the solution of this problem. Alpha 1 equal to, alpha equal to minus b plus minus root over b square minus 4ac by 2a. So therefore alpha 1, this equation has two roots. Suppose you consider this is equation 4. Equation 4. This equation has four roots. This equation has two roots. This equation has two roots. This equation has two roots because square, two roots. So let me say the roots are alpha 1 and alpha 2. But or you consider another symbol, lambda 1 and lambda 2. Okay, no problem, but it is good you consider alpha 1 and alpha 2. There will be a consistency, alpha 1 and alpha 2. Now you tell me the expression of alpha 1 and alpha 2. Alpha 2. Alpha 1 and alpha 2. So therefore alpha 2. Therefore alpha 1 equal to, we can write minus b plus root over b square minus 4ac 4ac by 2a. Everyone write it yourself. The solution of this root, alpha 1 equal to minus b plus a square root of minus square root of b square minus 4ac. This will be within bracket b square minus 4ac. This total part divided by 2a. This will be b square. Okay, alpha 1 will be this and alpha 2 will be will be minus b root square root of b square minus minus 4ac by 2a. So everyone write the solution of alpha, write the expression of alpha 2. So just you copy this part and you change the sign of the term. So minus b, this will be minus. So okay, so everyone tell me if you have any confusion or if you face any difficulty to solve this equation. We obtain a homogeneous second order differential equation, okay, to compute the transient response of this circuit. After that, we have derived its characteristic equation by considering some, actually by replacing some factors with other. Then we have calculated the roots of the characteristics equation in terms of alpha 1 and alpha 2 by using the simple actually formula. You know this formula. Now everyone put the value of B, A and C in the expression of alpha 1 and alpha 2. If you put the value of A, B, C in this equation alpha 1 and alpha 2, so you will get ultimate expression minus b equal to r by l. You see, I have written here b equal to r by l. Let me mark it by red color. B equal to r by l. A equal to, we have considered 1, and c equal to 1 by LC. Now everyone replace the value of alpha A, B, C in terms of our circuit components value, resistor, inductance and capacitance. So we can write minus R by L plus square root of square root of square root of, you consider within bracket minus r by l. So you just simplify 2a will be equal to 2 square root of, within bracket you can write r by 2l 2l whole square to the power whole square to the power 2 whole square minus 1 by LC 1 by LC. Okay, everyone compare your solution with this solution. The ultimate you will get alpha 1 equal to minus r by 2l plus square root of r by 2l whole square minus 1 by LC. Okay, alpha 1. Similarly alpha 2 you will get, you just copy paste this part and replace the sign, replace the and change the sign, change the sign. Okay, so this will be minus. So now we obtain the values of roots alpha 1 and alpha 2, and we know that the solution of this homogeneous equation is a1 exponential alpha 1 t alpha 1 t plus a2 a1 a2 are constant. We can calculate its value by considering the initial condition of the current and voltage. A2 exponential alpha 2 alpha 2 t. Everyone look at the solution part of the homogeneous equation. This solution is nothing but the transient response of the voltage, transient response of the circuit in terms of voltage, transient response of the RLC circuit. Okay, even, and we know that the value of alpha 1 and alpha 2. Now you tell me any confusion regarding the solution part of this equation. We have considered a RLC circuit and we have derived its differential equation by using Kirchhoff voltage law. The voltage drop for a closed loop. Okay, we know that the algebraic sum of voltage drop across a closed loop is equal to 0. After getting the differential equation for this circuit, we realize that this differential equation is a second order non-homogeneous differential equation. Therefore, its solution has two parts. One is steady state, another one is transient. And you know steady state solution is nothing but the value of the supply voltage. So no need to calculate the steady state response for this circuit. Now we need to calculate the transient response of this circuit. To compute the transient response of this circuit, we need to convert the non-homogeneous equation into a homogeneous equation. So how do you convert this non-homogeneous equation into a homogeneous equation? We just consider the supply voltage equal to 0, or we remove the supply voltage from your circuit. After getting the homogeneous second order ordinary differential equation, homogeneous second order differential equation, our next task is to compute the roots of this homogeneous equation, because we know that solution of this equation is a1 exponential root of this equation into t plus solution plus a2 exponential second root into t, because this is second order differential equation, therefore it has two roots, we know. So to compute the roots of this equation, we have considered its characteristics equation. And characteristics equation I have written here, the characteristic equation of equation 3 is like that. Let me mark it with red color, the characteristics equation. So after getting the characteristics equation, we can easily compute its roots by using the simple formula minus v root of square root of b square minus 4ac by 2a plus minus. Okay, so finally we obtain the transient response of the RLC circuit. Now my next question is that this equation has actually equation has RLC values. Okay, so by changing or the response characteristics of response will be changed according to the change of the values of RLC. Let me repeat this point. The characteristics of the response will be changed or may vary according to the change of the value of RLC, because alpha 1 alpha 2 this value depends on RLC. If you change the value of RLC or the properties of RLC, the characteristics of the response may change. So let us study that part. So see, okay, first thing, loss free circuit. What is meant by it? Loss free circuit means there is no resistance. That means that is R equal to 0. R equal to 0. Lossless circuit, you know that capacitor and inductor are energy storing element. Only resistance or resistor dissipate power. That's why resistance is a power dissipating element. So the power will be lost due to presence of resistor. So if you make the value of resistance is equal to 0, then there is no resistance in your circuit, therefore there is no loss. So you can say your circuit is free from loss actually. Free from loss. So loss free circuit, the condition is that R equal to 0. And for this case, what will be the response of this circuit? What will be the response for this circuit? If you make R equal to 0, then you will get alpha 1 alpha 2 equal to how much? Then you will get alpha 1 alpha 2 equal to only alpha 1 will be equal to only R is 0, then mean square root of 1 by LC. Okay, so alpha 1, everyone write the expression of alpha 1 and alpha 2 by putting the value of R1 equal to 0. So alpha 1 will be alpha 1 will be equal to, after getting the response, transient response of this circuit, our next task is to study the characteristics or variation of the response for different values of RLC. The alpha 1 will be square root of 1 by LC. Alpha 1 square root of 1 by LC. There will be a minus sign before this. A minus sign will be present here. 1 by, everyone try to understand the solution part of this equation, and after getting the solution or transient response of this circuit, our next objective is to observe the variation of the response for different values of RLC. Therefore, you will get, now you can write this actually minus within this bracket. Alpha 1, for alpha 1 is within this bracket, square root of 1 minus. So this thing we can write as square root of minus 1 equal to, you can write j imaginary part, and 1 by LC you can write omega. Just you write, say this is omega. Okay, omega equal to 1 by LC. Now you write the value of alpha 2, the expression of alpha 2, write yourself and tell me. Alpha 2 equal to, you can write square root of 1 by LC, and there will be no negative sign. Okay, so you can write j omega. Everyone see the condition. After getting the transient response of this circuit, we have put the value of resistance equal to 0. After implementing this condition, we can write alpha 1 equal to square root of minus 1 by LC, and alpha 2 equal to plus square root of 1 by LC, and 1 by LC is nothing but omega. Omega is the angular frequency of this response. Omega equal to 1 by LC. You can write this thing like this, or we can write F equal to 1 by 2 pi, omega equal to 2 pi F, so 1 by 2 pi LC. So this is the frequency, oscillation frequency of this circuit. So therefore, this response is known as undamped response for this circuit. The response, so if you put the values of this thing, of this factor, so you will ultimately get the expression VC. Here I have put I of t. In terms of I of t, you can multiply I of t equal to C VC t. So you just multiply C VC t and you just simplify, you will get such type of response. So therefore, this response is known as response, this transient response is known as, this transient response is called undamped response of the circuit. Undamped response. Undamped response of the circuit. This ultimate you will get this expression. Okay, so you know this thing. You know that ICT equal to d dt c vct vc t. So if you simplify this equation, so you will get the response like this. This is the transient current response. Current response. And you know I of t, let me write here, I of t equal to I of t equal to c dvc dvc t by dt. So ultimate you will get the expression of I of t, transient response, and from that response we can write this thing, I of t equal to Im sin omega. So here you note that the response of this circuit, transient response in terms of current, actually is a sinusoidal waveform, a sine waveform, and it's varying with a frequency f equal to 1 by 2 pi LC, and this response is known as undamped response. Undamped response. So next condition is that if r not equal to 0, any doubt regarding the undamped response for this RLC circuit, undamped response for RLC circuit? Okay. If resistance is 0, then means there is no loss in your circuit. No loss. So you can say your circuit is loss free circuit. You can say your circuit is loss free circuit or free from loss. So by putting this condition, the transient response in terms of current is nothing but a sinusoidal response, and sinusoidal response varying with time with a frequency f equal to 1 by 2 pi LC, or angular frequency omega equal to 1 by LC. If you have anyone has any difficulty to understand the oscillation frequency of this response, write your confusion in your chat box. You see, we have obtained f, oscillation frequency f, you know omega equal to 2 pi f. Let me write here, omega equal to 2 pi f. Angular frequency is related with linear frequency by this relation, omega equal to 2 to pi f. F is the linear frequency. So you can calculate f equal to omega by 2 pi. So omega f equal to omega by 2 pi, and omega equal to 1 by LC. So oscillating frequency for this response is 1 by 2 pi LC. Now you consider that r is not equal to 0. R is not equal to 0. Then what will be the characteristics or behavior of the transient response in terms of current? Everyone look at the next slide. So therefore here we will get total 4 situation for this circuit. If r equal to 0, then what will be the behavior of the response? If r not equal to 0, and that case there will there we will get three situation. If r not equal to is not equal to 0, is not equal to 0, then there will be four situation, three situation arise. Then three situation Asian will arise in the circuit, I mean response in the circuit. This three situation, let me write. You just see the expression of alpha 1 and alpha 2 within square root. You see r by 2l square minus 1 by lc. So you can consider r by 2l square 12 whole square greater than 1 by lc, one situation. Another situation, r by 12 whole square equal to 1 by lc. And third situation, r by 12 whole square less than 1 by lc. So let me write these three situation. Case 1, r by 2l whole square greater than 1 by lc. Case 2, r by 2l whole square equal to 1 by lc. And case 3, r by 2l whole square less than 1 by lc. Okay, so based on these three situations, the behavior of your transient response will change. Okay, so therefore basically there are first two conditions, r is equal to 0 or not equal to 0. If r equal to 0, then we will get undamped response or a loss free circuit. If r equal to 0, then we will get a lossy circuit, but types of loss: high loss, low loss, or medium loss. Okay, so depend on the factor within the square root. R by 12 whole square greater than 1 by LC, R by 12 whole square equal to 1 by LC, R by 12 whole square less than 1 by LC. If R by 12 whole square greater than 1 by LC, r by 12 whole square greater than 1 by LC, then you will get high loss. This actually indicates a high loss circuit. High loss circuit. And now you write its expression. This equal, then medium loss. And this case low loss circuit. Okay, and the corresponding response for first case is known as, this case is known as over damped response, this case critically damped response, and this case is under damped response. Which one I have shown here? This is under damped response for this case 3, r by 12 whole square less than 1 by LC, r by 12 whole square less than 1 by LC. This is under damped response. That case you see the sinusoidal waveform actually decaying exponentially with time, because the presence of this e to the power this term 80, a to the power 80. Everyone look at the present figure. This response represent the underdamped response for this circuit when the circuit has loss but low loss. The condition is R by 12 whole square less than 1 by LC, and you see the sinusoidal response, undamped response in this case decaying with trying exponentially because e to the power 80 due to presence of this term. If you simplify this expression by putting this condition, then you will get this expression. If you face any problem, you write in your chat box. Now let me show you the overdamped response or high loss circuit. For high loss circuit, the condition is R by 12 whole square greater than 1 by LC. The condition is, that is, this is the condition. Okay, greater than 1 more loss. This part is very greater than this part. This is energy storing, this is energy dissipating, and here you look at that the response decays, okay, and it takes a long time. The response decays slowly. You just change this thing. Here it will be I of t, not L of t. This actually I of t. I of t. Everyone, this is the current response actually. Current response. You just correct it yourself. You just correct it. Okay. This is I of t, and this is overdamped case. And let me show you. See, for this case, the response becomes 0 after a long time. After a long time, you will get the expression here. This cos hyperbolic terms and sine hyperbolic term present. So it will take in infinite time theoretically, but practically it will take much time to reach zero value. And finally, let me show you when these two terms are equal, medium loss or critically damping response. Critically damping medium loss, critical damping case when R by 12 whole square 1 by LC. You see this case, this start initially it's actually increases from low value, then it gets a maximum value, after that it decreases. You see k1 plus k2 e to the power 80. So this you see this term, if you multiply you will get k1 e to the power minus 80, that means exponential term. But for second term you see there is a linear term, t is present. So this term actually you will get first maximum value and then decays. Okay, so now I hope everyone understood the solution part of RLC circuit, especially transient response of RLC circuit, and after that the behavior of the circuit and its corresponding responses. High loss circuit, low loss circuit, medium loss circuit, loss free circuit, undamped response, overdamped response, critically damped response, and underdamped response. And I personally suggest you please understand the behavior of underdamped, overdamped and critically damped response. Overdamped and these two are actually a little bit confusing, complex. So you try to understand these two things. You see the response part, transient response part. If you notice for overdamped case, you will see that there is cos hyperbolic term present or exponential term present, and it takes a long time to actually reach zero value. But for critically damping, you see response part has two parts, one exponential and another part is a linear part, t terms present. So due to presence of t term, it actually initially increases. After getting a maximum value, then it will decreases. So that's why you get such type of card. Initially increases, then maximum, then decreases. Okay, thank you everyone. If you have any doubt, any confusion, write your confusion in your chat box. In your chat box, sorry. Okay, I will provide you some sample question for MTA exam within 2 days. Okay, thank you everyone. And if you have any doubt to understand the transient response of a RL circuit in presence of DC excitation, write in your chat box and let me explain that part. Okay, I hope everyone understand. Thank you everyone. Let me stop today's lecture here.